The next data center may not sit beside a river or behind a power substation. It may orbit above Earth with solar panels spread like wings, server racks sealed inside pressurized modules, and giant radiators glowing faintly against black space. The idea sounds extravagant until you look at what artificial intelligence is demanding on the ground. Enormous amounts of electricity, land, cooling equipment, transmission capacity, and political permission. If Earth is becoming a difficult place to build compute, why not move the compute somewhere else? That question is attracting real money. Companies developing orbital computing have announced ambitious plans and new financing. Their pitch combines three trends. Launch costs have fallen compared with the past. Solar energy is abundant in orbit. And demand for AI infrastructure appears almost unlimited. But funding a plan is not the same as deploying a giant working data center. The engineering gap between a demonstration payload and industrial-scale orbital compute remains enormous. Start with the strongest argument. Sunlight. A satellite in an appropriate orbit can receive intense solar energy without clouds. Nighttime weather. Or local grid congestion. Solar arrays already power communications satellites and space stations. If a computing platform can generate its own electricity in orbit, it avoids waiting years for a new terrestrial power connection. For an AI company desperate for capacity, time can be as valuable as energy price. Yet sunlight is intermittent in many low Earth orbits because the spacecraft repeatedly enters Earth's shadow. Batteries must bridge the dark periods, or the system must reduce workload. Higher or specially chosen orbits can improve exposure, but introduce other trade-offs in radiation: latency, launch energy, and maintenance. Solar panels also degrade, need structure, and create drag or attitude control challenges. Space solar power is real, but it is not a free, infinite outlet. Cooling is the most misunderstood part. People hear that space is cold and assume a server will naturally stay cold. In fact, vacuum makes cooling harder in one crucial way. There is no air to carry heat away. On Earth, data centers move heat into air or water. In orbit, waste heat must travel through conduction inside the spacecraft and then leave as infrared radiation from large surfaces. That means radiators. Every watt consumed by a processor eventually becomes roughly a watt of heat that must go somewhere. High-performance AI chips pack huge power into small areas. The radiator must operate at a safe temperature, face the right direction, avoid too much sunlight or reflected Earth heat, and survive micrometeoroids and debris. A megawatt-class orbital data center could require radiator area that rivals or exceeds its solar array area, depending on temperature and design. The Stefan-Boltzmann law governs the basic trade-off. Hotter radiators emit much more energy per square meter, but electronics, coolant, materials, and reliability limit how hot the system can run. Raise the temperature, and the radiator shrinks, while component stress increases. Lower the temperature, and the radiator grows. The most futuristic-looking part of an orbital data center may not be the computer. It may be an enormous folding thermal wing. Then comes mass. Servers need chips, memory, networking, power conversion, shielding, pumps, pipes, structure, batteries, solar arrays, radiators, antennas, and redundancy. Every kilogram has to be launched. Reusable rockets can reduce cost, but launch remains expensive and capacity is limited. Recent industry reporting has emphasized how constrained suitable launch options can become when many customers want the same rockets. An orbital data center competes with satellites, exploration missions, national programs, and other infrastructure for space on the manifest. Hardware also fails. On Earth, a technician can replace a fan, cable, power supply, or entire rack in orbit. Repair may require robotic systems. modular replacement spacecraft. Or human servicing, radiation can flip bits and damage electronics. Thermal cycling stresses materials. Atomic oxygen affects surfaces in low orbit. Debris moves fast enough to puncture vulnerable structures. The design must assume failures en route around them without turning every broken accelerator into permanent dead mass. Upgrades create another economic challenge. AI hardware evolves rapidly. A terrestrial operator can install a new generation of chips and move older machines to less demanding work. A satellite designed today may launch after its processors are no longer state-of-the-art. Modular payloads and frequent replacement could help, but then launch and disposal become continuous operating costs. Orbit rewards long-lived hardware. AI economics often reward fast replacement. What work would make sense in space? Not every AI request needs to leave Earth. Sending data to orbit and results back introduces latency, bandwidth limits, ground station dependence, and communications cost. Interactive services for users on Earth may be better served by terrestrial data centers. But tasks that already begin in space are different. Earth observation satellites generate huge images. Instead of transmitting all raw data, an orbital processor could identify fires, storms, ships, crops, or military activity and send only the valuable result. Other candidates are delay-tolerant workloads, model training, scientific simulation, batch inference, or specialized processing that can run when power and communication are available. A company might also place compute near a future lunar economy or other spacecraft. In those cases, avoiding a round trip to Earth can be valuable. The first successful market may therefore be compute for space, not move the entire terrestrial cloud into orbit. Security cuts both ways. Physical access is harder in orbit, which sounds protective. But the platform depends on radio links, ground stations, navigation, and remote software updates, jamming, cyber attack, supply chain compromise, or anti-satellite conflict could interrupt service. A failed terrestrial data center can often be reached. A failed orbital platform may become inaccessible while still carrying sensitive data and valuable hardware. There is also an environmental ledger. Moving electricity demand off a local grid could reduce pressure on water and land in one region, but rockets produce emissions. Launches create noise. Manufacturing consumes materials. And large constellations add collision risk and astronomical interference. Spacecraft must be deorbited or moved to safe disposal orbits. If the plan involves hundreds of large platforms, sustainability cannot be measured only at the data center site, because the site is now an orbital shell shared by everyone. Economically, orbital computing must beat more ordinary solutions. Terrestrial chips can become more efficient. Data centers can move toward renewable generation, nuclear power, colder climates, or regions with spare grid capacity. Software can reduce computation. Utilities can build transmission. Waste heat can be reused. An orbital system does not compete with today's most constrained project forever. It competes with every improvement Earth can make during the years required to deploy it. Still, extreme demand can make strange options rational. If AI companies value a megawatt of new capacity so highly that they accept enormous capital costs, orbital systems gain room to experiment. Governments may fund dual-use computing for defense and Earth observation. Launch providers may design rockets around regular infrastructure delivery. Robotic servicing may improve. A demonstration that looks uneconomic as a cloud replacement could still unlock technology for other space industries. The right way to judge the field is by milestones, not renderings. First, can a payload run modern accelerators reliably in the radiation and thermal environment? Second, can it reject heat at meaningful power density? Third, can it move enough data at acceptable cost? Fourth, can modules be launched, assembled, serviced, upgraded, and retired safely? Fifth, can the total cost per useful computation compete with a terrestrial alternative? Each milestone should be measured at the same scale as the claim. A small satellite running an AI model proves that computation works in orbit. It does not prove that a gigawatt data center is practical. A successful cooling panel proves a thermal design at one load. It does not prove that a fleet can manage thousands of accelerators. Scale changes structure, launch cadence, debris exposure, communications, and economics. Networking deserves its own milestone. A data center is valuable because machines communicate at enormous speed. Inside one orbital module, optical links may provide high bandwidth. Between modules, laser crosslinks could create a distributed cluster. But cloud users on Earth still need uplink and downlink capacity, spectrum coordination, ground stations, weather resilience, encryption, and routing. A computer with abundant power but a narrow communications pipe may spend much of its time waiting for data. Assembly strategy changes the design. One giant launch simplifies in-orbit connections but demands an enormous rocket and creates a single failure point. Many smaller launches spread risk but require rendezvous, docking, fluid, or thermal connections, networking, and autonomous construction. Every connector must work after vibration, vacuum, and radiation. A loose cable on Earth is a maintenance ticket. A failed orbital connector can strand millions of dollars of hardware. Finance will test the schedule. Investors may fund prototypes on the assumption that launch prices continue falling and AI demand continues rising. If either trend changes, the economic target moves. A terrestrial data center can often be built in stages and repurposed. An orbital platform commits capital years before revenue. Contracts with governments or space data customers may therefore matter more than speculative demand from ordinary cloud workloads. Regulators will need plans for collision avoidance, radio use, remote sensing, data jurisdiction, and disposal. A platform may process information gathered over many countries while physically passing above them. Sensitive workloads raise questions about export controls and national security. The rules will not be an administrative footnote. They may determine which computations are allowed and where results can be delivered. Orbital data centers are therefore neither a joke nor an inevitable future. They are a serious response to a serious terrestrial constraint. Wrapped in one of the hardest systems engineering problems humans can attempt. Their best early applications may be narrower than the headlines, and that is normal. Transformative infrastructure often begins by solving the one problem for which its disadvantages matter least. AI may eventually leave Earth in a meaningful way, but it will not escape physics. Every computation still needs energy. Every joule becomes heat. Every kilogram must be launched. Every bit must travel. And every machine placed in orbit becomes part of a crowded environment that no company owns alone. The first useful systems may look disappointingly small. A few accelerators processing satellite images, testing thermal hardware, and proving that remote upgrades work. That modest path is not failure. It is how engineers discover which assumptions survive contact with orbit. A credible company will celebrate measured performance, not hide the difference between a prototype and the megawatt architecture in its concept art. If those experiments succeed, scale will arrive through repetition. Standard modules, known connectors, predictable launches, shared servicing, and workloads designed around orbital constraints. The revolution, if it happens, will be less like launching one giant computer and more like learning to operate a new kind of utility. The dream is a server farm under endless sunlight. The reality will be decided by the shadow, the radiator, the rocket, and the repair robot.